Okay. This is the lecture that goes into the details of the relationship between rotational energy surfaces, symmetry, characters, representations, and things for rotors. In particular, the rotors that we talked about last time in lecture 25 were symmetric, rigid quantum rotors, as opposed to the classical ones that are also described by Hamiltonian that would look like that. The idea today is to show a connection between the rotational energy surfaces, the representations that make them and use them, and also do then a very different rotor, the asymmetric, kind of the opposite of the symmetric in some ways, to get a good feeling for what we use now to solve some really difficult angular momentum problems that involve molecular rotation. But these methods are applicable as well to electronic, vibronic, vibrational, and other things that we have in mind. Now, I started this business of the tensor expansions. We're going to carry that through. That's also used for these high-powered molecules. And I would like to now do some detailed analysis, both using the operators and the character analysis. We'll do that first. Obviously, that's your the idea is to get the characters to tell you what's going to happen, and then that aids you in the detailed calculation. So we've already seen this with respect to D3. Today we're going to use a smaller group, which is the symmetry of the asymmetric rotor. The 4 group, D2. We'll go through and analyze levels in terms of that. And once we get done doing this, we'll have, I think, a much better idea of what's happening and what we've been talking about, these level clusters and things that happen for these much larger and more symmetric rotors should become clear. So let's go ahead and do the review part of this just to get us started here. Once again, a listing of applications that work for this. So let's take a look again at a symmetric rotor Hamiltonian, and its way we look at it using the rotational energy surfaces. And the symmetric happens to be an exact geometry for the quantum mechanical eigenvalues. And as far as it goes, the phase space, the quantum phase space, is really what this is. And the basic idea of this plot of the Hamiltonian is to make its energy be plotted radially. So this is the lowest energy region down here, and then as the radius increases, that's the highest energy you can achieve on the surface. And this is an energy that's being plotted versus the direction of the J vector in the body frame, as opposed to the lab frame. This is the bod frame here that we're looking at all of these rotational energy surfaces, subject to the constraint that the magnitude of the angular momentum, that's the angular momentum quantum number for us, is constant. So that's fixed while we test different directions of the J vector, which corresponds to picking more or less the different angular velocities, rotation directions for the object in question. So the idea of that is that it's connected to the angular momentum cones, which are plots of the magnitude being J plus a half, approximately square root of J times J plus 1 exactly. And each of those cones has a cross-section that's indicated here And the idea is where those cones intersect this rotational energy surface, that's a particular energy, that's a quantum energy, that's this quantum energy right here. And so the geometry that we're looking at, as we were working with last time, gives an exact quantum eigenvalue for that case. Now all of the things that we'll be doing, starting with the asymmetric top, this is an approximation. But nevertheless, it turns out to be a very useful and quite accurate approximation. An accuracy that improves as you get closer to parts of the rotational energy surface that have a mutual, that is a rotational, local rotational symmetry. Anyway, a lot of this stuff is in this paper, a very recent paper, in the International Journal of Molecular Science. So you'll see the references to that, and the older textbooks have mentions of this too. So here are the energy levels listed in the way they normally are, stacks of lines representing quantum eigenvalues, and the two extremes of symmetric top are this oblate top here is an object that's shaped like a frisbee and has more inertia around this axis, what you could call the z-axis if you want to look at it horizontally, than it does around the axes perpendicular to z-axis, say y and x, or this would be x and that could be y, if that was z coming out this way. That's sort of an opposite in terms of the values of the parameters to this one, which would be an object that was an elongated, say, some kind of linear molecule that was of a structure that could allow to be called a symmetric top. And that is a top whose two inertial constants are equal, and the other one is either greater than or less than these two here. Now they're inverse inertia, remember that, because as the inertia goes up, and indeed for a diatomic molecule, the inertia goes toward zero as you become longer and skinnier, and as this approaches zero, this approaches infinity, and so all of the levels that are off the equator of the rotational energy surface go to a very high value, or to essentially infinity, and therefore that wipes out any description, any structure in the body frame. Okay, now another thing let's never forget is that all of these levels that remain here, even after all the n levels have gone to infinity, have the laboratory degeneracy of 2j plus 1, but what we're working with and showing here are a body frame degeneracy, which is the other side of the Mach-Mach duality. So Angrumentum 2 has 5 levels exposed here, but each one of those is 5-fold degenerate. So there's 25 states hiding on just j equal 2 and so forth. Okay, now I mentioned that a good deal of this is in chapter 23, unit 8 of the quantum theory for computer age, and this particular figure, in fact, is there. A figure like this one is also in the Principles of Symmetry, Spectra, and Dynamics of the 1993 book, which is much older. This stuff doesn't get old as far as I can see. It is really a beautiful thing that you're going to see here, particularly as we start to look at an asymmetric top and its structure, which is really the topic of the day. And the asymmetric top that we'll look at will be right in the middle between these two, the most extreme, most asymmetric top, one that has about equal amounts of the prolate and oblate regions of phase space. And this is just one that's sketched. This is a sketch I did. These are done very carefully with a computer. I actually sketched the levels onto this one for j equals 6. And we're going to analyze that. And the question that we will answer is, how do you predict that you have that spectrum right there that consists of 4 A1s of D2, 3 A2s of D2, 3 B1s of A2, and 3 B2s of A2. And what do those A's and B's, 1s and 2s mean for a rotor that's having its angular momentum cutting these curves, and why do they go like left-handed instead of right-handed? We'll discuss all of that as we go through this. But in any case, the asymmetric top is the one which has deviations, very strong deviations from intersections with a circular cone. It makes a very scrunched up cone. Now in general, what we're trying to get across here is that the rotational energy surface and the multiple tensors that come out of these expansions of Hamiltonians, essentially rotational energy surface is a snapshot or a drawing of the particular tensor combination that a molecule might have. And the whole motivation here is that these sort of analyses are really pretty much beholden to the black box of a computer matrix diagonalization of a nonlinear. So you feed in a Hamiltonian, and all sorts of things are happening inside the black box, and then out come a list of the energy eigenvalues, and if you really work hard at it, you can also get the energy eigenvectors. The question is, how do you understand what came out of that black box? So the whole idea is not only to just calculate things, but also to visualize them. So the most complicated Hamiltonian we'll consider in this course would be a linear combination of scalar, say, the 3 vector components perhaps, then whatever can be coming out with various rank tensors that might be useful and have some sort of rotational energy surface. And of course it's when you combine these things, when you add these things up, that you get some particular, in this case, a mixed up rotational energy surface. It isn't just a single tensor. But still, you can use these methods that we're talking about to analyze the spectra of it. Now we've already been through the expansion here, but this will let me remind you that what we're dealing with is bang versus buck. Bang for a buck, that's a very American expression. I call this momentum 101 and energy 101 for rotational analysis. This would be your linear and momentum and energy, but we're talking about angular momentum. We use J or L or some other letter near that in the alphabet, like K sometimes, for an inertia times an angular velocity. And the energy that we're plotting is in the Lagrangian form, an inertia times omega squared. But Hamiltonians, you see, are in terms of momentum. So we're talking about J squared over twice the inertia as our expression for kinetic energy here. So there's that inverse inertia that I was talking about. And that's what these constants are. Their coefficients that are like 1 over inertia. And this lecture 25 derivation here was just showing the expansion that goes with just this much of a rigid rotor Hamiltonian that had no symmetry to start with. Its multipole expansion consists of a scalar, spherical thing, just the J squared would be a sphere, right here, with that coefficient, if these are the inertia parameters. And then to the next level, you add a thing that is 2c minus a minus b coefficient, and this is multiplying a symmetric top symmetry. So this would be specifically a case where I had a equal to b, but not equal to c, you see. So this would just boil down to a difference between 2c and 2a divided by 6, so it would be 1/3 there times a minus b. And this is the tensor that you would have. But then if the symmetry is further reduced to this extreme case of being asymmetric, having all three parameters different, then you add just this particular tensor, T2 plus T minus 2. This one is T2, 0. So this, and this, but that combination plus the scalar makes up all you need to describe a asymmetric top in its eigenframe. You see, the cross terms that you would add to this for doing a completely randomly chosen in a body frame is more than this. But this is all you need to do the analysis that we'll be doing. So that's the most elementary expansion. Now, in the next lecture, and pretty much if we maybe have 2 additional lectures, we could really cover this well, but we're at least going to try to show you a generalization of the spinor analysis we spent a lot of time describing when we were talking about spin vectors and spin a half. The generators that we had there, as you recall, were sigma x, sigma y, and sigma z, but the names that we're giving them in terms of tensors would be the vector notation T1, 1, T1 minus 1, and T1, 0, that are complex combinations, these two, of x plus iy and minus iy. So that is the coefficient b plus ic times that guy, and this is b minus ic times that, using our old a, b, and c and d parameters. And then this one is just T1, 0. Okay, and then these things here are the elementary raising and lowering operators. Okay, so that's our description of a 2x2 Hamiltonian. 3x3 Hamiltonian has also a scalar and a vector set, but it then has a tensor set in additional to that. A 3x3 matrix that wasn't Hermitian, you could say, has 9 parameters, and indeed that's how many operators I have here. So in addition to a scalar and a vector, there is the tensor next. And then this goes on. If I want to do 4x4, I'm going to add another row on top of this that has an octopole. You see, this is a quadrupole, and this is the dipole, and there's the monopole, you see. So this really is in the spirit of the spectral decomposition that you see using Legendre polynomials. And that's something else we would like to describe a little bit before we finished with this course. But most of this is stuff that would go into a second semester. So we're pushing the edge here a little bit to introduce these things, but I want to do it in any case. Now, with respect to our rotational energy surfaces, which, as I remind you, are plots of the direction of a vector that doesn't change its length, and that's what a free rotor would do. It would not change the length of the angular momentum vector. That's going to be conserved because in the lab frame, the angular momentum vector in a classical sense would be fixed to the stars, both in direction and length. But the length of it will be the only thing that's maintained in a body frame. That vector will move all over the place. And that's true classically. Even if the angular momentum cones were to be very tiny because we're working with quantum numbers that are astronomical, we still would have the J moving around in a classical sense. That's called recession. And rotational energy surfaces tell where those classical paths would be simply by intersecting a constant energy sphere with the surface. So each time we do that, there will be an angular momentum cone that's the closest angular momentum cone to a particular trajectory. The one that goes equally inside and out of it is a pretty good approximation to the quantum state that the thing has there. And as you get closer to the top, you can do that with great precision. Now, the idea of using the left hand to tell how this thing moves classically is very nice. If you're on a high part of the surface, you stick your thumb high, and that's the direction that the angular momentum vector will precess in the body frame. And then if you want to find out what's going on down in the valleys, you point the thing down, and now you're going to see the angular momentum vector precessing in that direction. Now it's going clockwise. So it's clockwise around a low, not too different from our weather in the northern hemisphere. It's counterclockwise around a high, sort of what the Australians and the people down south would use.
Does that have its root in that negative azimuthal quantum number?
You bet it does.
Okay.
Yes, thank you for that question, because when we looked at the quantum number n with our Mach procedure, we discover that it's minus because, as I said before, the people in the body frame see the universe going this way for a transformation the universe sees going the other way. So all that's important here is the relative motion of the two, right? But you can get that relative motion by moving the body this way, or you can get it by moving the laboratory this way, you see, the world, the universe, okay, in our funny way of making fun of Mach, okay? So, yes, that's why the left-hand rule is applicable to this. And then for angular momentum 3, which we were just showing a picture of a rotational energy surface, there are the cones that go with us. And remember, there's a plus and minus cone for anything except the equatorial one, which has no component on the z-axis. The n equals 0, or for most molecular people, use a k to describe the internal angular momentum quantum number. That's what I'm using right here. So get used to that. Then here's the two extremes of symmetry, symmetric and asymmetric, for something that's a uniaxial rotor. We're going to have some that are multi-axial, starting with the asymmetric one. All right, now, level splitting. Let's just go back to the lecture. This is a review of a D3 page, namely the page 58 in lecture 15, where we took the D3 symmetry and showed how to calculate the splitting due to D3 symmetry in some kind of trigonal perturbation on an angular momentum level, atomic level, could be a scalar with just one, that's a singlet, could be a triplet with the letter P for angular momentum 1, that's 2L plus 1 equal 3, okay, and then 2L plus 1 equal 5, that's the D quintet. Angular momentum 3 that we were just talking about, the F septet, there's 7 of those, okay. They're all degenerate if there's only isotropy. If there's only O3 or R3 symmetry, then all of these are degeneracies, these 2L plus 1, for the spectra of a given L or J. Okay, so for L equal 4, we've got 9, a known net. It's called the G orbital, and that's the last time that the letters actually make sense in terms of old-fashioned spectroscopy. Anyway, the idea is to calculate what irreducible representations of this lowly D3 symmetry result from this particular representation of the great R3 or O3 rotational three-dimensional symmetry, a spherical, if you will, symmetry that's experiencing some sort of discrete perturbation that's only got degeneracies of 1 or 2, and here we're talking about a degeneracy of 9 or 11 or something like that. It's going to split, and how much. So we get the characters for this monster symmetry from a single formula. This one, in terms of the angle of rotation, that's all it cares about, because all rotations of a given angle are in a same class with all the others that have that same angle in this group. That's not something that you find in the discrete groups, like the octahedral or the D3. So you write down the U2 R3, that's the rotational group, or O3 characters, and these just using this formula right here. And D3 was interested in 120 degrees and 180 degrees, and of course everybody's got 0 degrees, no matter how lowly the symmetry is. And so we look at each one of these, and then we pick a particular one, and we discover that that particular one has an A1 and 2 E's for D3. Okay, and I was just showing trial and error in this particular page. The whole idea was to get you used to this formula here, which lets you do higher values of angular momentum. But trial and error is good enough for the first few levels that you encounter. And you need to have the D3 character table in order to correlate with the big group's character table and make this induction or subduction table, this correlation table between the representations of the big group and those of the little. And the F stands for a frequency of a particular thing, like this one's showing up twice in the angular momentum tube. Okay, now what I want to do is do this whole thing with D2. Okay, so the character analysis of an orbital splitting. This is good for atomic and molecular physics, both. They have very different physics. But I'm just going to take L equal 1. Okay, it has 3 levels. What do those split to for D2? Okay, and the D2 consists of just 180-degree rotations around X, Y, and Z. That's all it's got, besides doing nothing. So it's a 4 group. So it's 4 elements if you count the identity. But in any case, the characters for the D2, which there's character table right there. Character tables are all 1s and -1 because it's C2 cross C2. There's a C2 subsymmetry repeated 3 times, and then repeated again with a minus sign. That's what you get when you take the cross product of C2 with itself. So you have these labels A and B, that's even and odd in a particular axis, and you can see that that's the y-axis that's being talked about when you say A for plus and B for minus. But then there's the x-axis that determines whether it's 1 that's even or 2 that's odd. And here it's even again, and there it's odd again. So those are key columns to determine the symmetries that are being described by D2. The third symmetry with respect to Z is the automatic product of the symmetries that you got for these two, you see. Like this one times that one makes that one, this one times that one makes that one, this one times that makes an even out of 2 odds, and so forth. So there's a binary arithmetic that's built into this 2-bit, shall we say, symmetry, computer symmetry. All right. Now, what we're going to do is we're going to take angular momentum 1, and we're going to find out, just by looking at these two tables here, what the orbital content is for angular momentum 1. Which of these actually get to participate? And only 3 of them can, because that's all I've got. Here, I only got a dimension of 3. I can't use all 4, but which are the 3 I'm going to use? Okay. Well, you can see by trial and error that if I take, leave this one out and take this one, and this one, that is, put a 0 on the A1 and don't have any of that, but just have 1 each of the others, that adds up to 3 minus 1 minus 1 minus 1. So it takes a few tries to get that. It's pretty easy to see that that's the answer. I get 1 A2 right here. I get a B1, and I get a B2. That's the content listing of this particular orbital, p orbital, angular momentum 1. And there's a picture of it split, mentioning that A1 is not used, but the other 3 are. Okay, so that's a crude introduction to character theory for this group D2. We can certainly do better. As we go to angular momentum 2, now it's 5 things that we might be getting. And now I should point out what this formula was giving us. If you put into the values of the 180-degree angle for this formula, you're either going to get all minuses, because they're all 180, and that's all this formula knows, and you're going to get all pluses. And that's the way it should be, because they're twofold symmetric rotations, and so all we can do is go even, odd, even, odd, even, odd forever. So this particular table has a very simple structure for D2, as you can see. And this particular one's coming up with ones for even. Okay, the 3 is coming up with odds. So the separation between j equal even and j equal odd becomes very obvious at this point. It is also very obvious in some other sectors. Okay, so we take a look at this thing. Now, trial and error would finally yield this answer, but already you see it's a lot of different possibilities. So I'm going to just jump right here and say the F formula is much better than trial and error. And all you have to do with the F formula is take these 5 and the 3 1s and do a multiplication, a scalar product, and that's, you see, all you've got here, because the order of the class is not weighting anything but 1 here, you see. And we're just subbing over elements, not whole classes, so that makes it really very simple. And it's real, so you don't even have to worry about the star. Okay? You just have to worry about 1 over the order of D2, which is, of course, a 4 group, is order 4. So I have to do 1/4 times the scalar product of that vector with that vector. Okay? That is 5 plus 1 plus 1 plus 1. That's 8 divided by 4 is 2. So A1, this one, is going to show up twice. So there's your answer. That's where I get the 2, the frequency of A1 in angular momentum 2. All right? Then the other ones, and they're all the same. I just can get the same thing for all of them at once, because they all have the same characters over here with respect to this rotation of 3 dimensions. And I get a scalar product here of 5 minus 1 plus 1 minus 1. Okay, so that's 5 minus 1 is 4. 4 divided by 4 is 1. Every one of them has 1 frequency repeat. Okay, pretty simple. All right? And obviously this is much better than trial and error. Okay? And so we can go ahead and do a few more. Here's angular momentum 3. Okay? And you look and you see that this particular scalar product gives me 7 minus 3. That's 4. Divided by 4 is 1. So I get 1 of those. I went up in thing, but I lost my scalar by dealing with an odd fellow. Okay? But then 7 plus 1 minus 1 plus 1. Okay, 7 plus 1, 8 over 4 is 2. So I get 2 of every one of those. 2, 2, 2, 2, 2. Okay? In any case, here's the L equal 2 splitting. This one is too numerous to really draw in the little space that's left there, so we'll come back to it later on. In any case, this goes forever. Okay? Now, we're going to talk about this with respect to the octahedral group, but there is some amazing things going on here. And I think what's really interesting about this is called crystal field group theory, because the crystal could have D2 symmetry in this case, or octahedral in the case of famous solids like sodium chloride, or tetrahedral, or any of the crystal point groups. You see, they're going to have this arithmetic. And this arithmetic was put together by Hans Bethe. It's one of the most famous of the physicists. He was an advisor for Richard Feynman when he was at Cornell, sort of a mentor for him. He lived to a ripe old age in the 90s, late 90s. He was really prolific, but he was somewhat without an artistry. When it came time for him to name representations, he would just name them gamma 1, 2, 3, 4, 5, 6, 7, 8, 9. No way of distinguishing them in any particular way. Now, the numbering and lettering scheme for representation, I've already criticized it since it is just like the lettering scheme for spectroscopy, P, D, F, G, I mean, sort of meaningless. The attempt to get away from that is, I think, really important. Having A1 and A2 and 1s and 2s and things and getting used to them on the basis of this character table is important. And so that's why I criticize what he did. Now, one of the things that amazed me when I learned about the crystal field theory was just, what's happening here? He would never carry his tables very far. He didn't have to. But in molecular physics, you do have to, because you can have angular momentum of 100 or 200 or 1,000 even. And so it just bothered me that, you know, how could I account for this plethora of levels that are coming out? And there's a way to do that that's really beautiful, and that's what rotational energy surface analysis gives us, finally, after you've looked at it enough hours. So we're going to be talking about that fairly quickly, just with respect to asymmetric rotor levels for high J. But before I do that, I want to go ahead and do some of the guts work, some of the real grinded out angular momentum operator work that's needed to produce a Hamiltonian matrix for J equal 2, 3, 4, 5, 6, even low J's, but certainly also high J's. What do you do? Okay, well, we have the formulas already for us. We made this connection between the two-dimensional harmonic oscillator with U2 symmetry and the angular momentum operators that correspond to products of the creation-destruction operators in up and down pairs, like this, and the computation relations and stuff that go with them are behind this. We don't need to look at those anymore. We just write Jx as 1/2 of J plus and J minus. J plus is Jx plus Ijy, J minus Jx minus Ijy, so it's just the inverse of these two. Okay, and it's the angular momentum matrix elements of x and y that really make things happen. The z part is very trivial. It's just a combination of the number operators for this thing. But in any case, this little mnemonic of Friedman is the thing that makes our formulas. So this was from lecture 24. You should go back and look at it. It doesn't make any sense. This n plus 1 here is just placed j plus m times 1, and then j minus m is n down. Okay, so there's a half sum and half difference relationship between j, m, and n up and n down, analogous to that. So what we do is we, if we're working in a laboratory, ordinary atomic physics, we would simply do Jx equal a half sum of plus and minus, who has eigenvalues that are shown there and there respectively. Okay, and then this one has a little minus I here, so I got to put that in front, and I would do a difference, you see, of those two matrix well, they're not eigenvalues, but they're matrix elements. Then Z, no problem. It's just M. Now, here we are using the Mach states. But the idea is if it's a lab, then the internal BOD quantum numbers will not change. You might as well just leave them off. You're working in the laboratory, you never know they're there. But the same is true, essentially, for the body. Okay? I use 3 letters for BOD. It's kind of a California term. It's a little obnoxious, but bear with me. Anyway, they're the same, except they all do stuff with the N's, and the M's don't change. So the laboratory stuff, it might as well not be there if we're working with a pure body operator. But you can use these formulas virtually unchanged, with one change. The Y matrix element will be conjugated. That's the only difference as far as raising and lowering goes. Okay? And if we do this trick we did before, we don't even have to put a minus sign on the N. I will leave that off for that reason. So that's a little bit of chauvinism right there, but we're going to respect the laboratory as far as being right-handed and take that minus back. In any case, there's a plus I there instead of a minus I. It's the only difference. And that's a good thing to remember because you can take calculations you've done on the laboratory and put them out. Anyway, this is what happens when you get the, we're after jx squared, jy squared, okay, and then jz squared is an easy one. That's just being given a term in the middle there. Anyway, I go through and I do jx squared, that's equal to the jx eigenvalue times jx. So then I've got to get 2 terms, okay? Same thing for that one, and so forth, adding them all up, gives me a matrix element for the Hamiltonian with these formulas. And we could spend, you know, at least half of the period going through and making sure every one of those is right. And then the same thing goes for the application of the formulas. But I just want you to see that this is all there is to it. This is all there is to it. Making a Hamiltonian for any J, however big. Okay, it's just a question of how many things you have to write down, and it's 2j plus 1 squared. So that's what's coming out here in a detailed note. So we'll just do j equal 1, and we'll analyze very carefully the results of that. We'll look at j equal 2 and look at a pretty good picture of what they are. Then we'll consider high j using the rotational energy surface plots. So we're going to take the asymmetric top pretty seriously for a little while here, and that will get us set the stage for doing it with these big molecules. So here's Jx. We've already seen these actually written out explicitly. Of course, Jz is diagonal, with 1, 0, minus 1 for angular momentum 1. We're going to do the matrix for a parameter A equal 1, B equal 2, C equal 3. That's a most asymmetric top. The difference between 2 and 1 is the same as the difference between 3 and 2. B is exactly between 1 and 3, and that makes it the most asymmetric. We'll see the geometry of that later. But in any case, here's these matrices. Now you can just square the matrices and you get this. Okay? But that formula would also give them. It's a good check from the formula. Okay? And that's true no matter how big the matrices are. Squaring the matrix is a quick way on a computer to get these things. Make the J formula work without all those extra terms. In any case, here's what the whole Hamiltonian looks like. Okay. Now, let's go back and look at our symmetry analysis. What we could have done is instead of just using the straight angular momentum things, we could use the projection operators of D2 to get an A2 and a B1 and a B2. That's all we're going to be seeing here. And I could find the eigenvectors of this by symmetry. I didn't do that. I'm just looking at this thing and saying, it's a pretty simple thing here. This is equal to that. So we're going to get a half sum and a half difference of 2 of those states, namely the plus and minus 1, or plus n equal plus and minus 1 states. Here are the eigenvalues that result. There are the plus and minus, square 1 over the square root of 2. The one in the center here is already diagonal, okay? So we don't have to do anything with it. A plus b equals 3 is the result for these particular values of the parameters. Okay, this is a general case for any set of parameters. All right, now, here are the three states that we're going to use. We're not going to use that one. It's not showing us anything. It's not correlating, but the other three are. Okay, so it's A2, B1, and B2. What do they mean? All right. Now, when you look at this thing, you ask yourself, these are three vector components, x, y, and z, which one? And you know that a rotation by 180 degrees, or any angle, around the x-axis does not affect the x-axis. Okay? So, a minus and a minus, that's not what we're talking about, but this one is telling us that this B1 really means x-axis. It's an x component of a vector. An x component of our generalized rank 1 tensor, if you want to use all the fancy terminology. So there's the B1 being x-like. There's the A2 being y-like. And there's the B2 being z-like. So that's another name that you could put on these group representation labels. Okay? And you can see it too. This state right here is very z-like. It's the two p balls, if you will. This is the wave amplitude, okay, not the square of it, not the probability. This is plus phase, minus phase, so it's a vector pointing on the z-axis, and it's B2. You see, that's the B2 state there, which is the z one. It's the one that's diagonal. It's the one that has that eigenvalue. Okay? And then you go on to the other two. There's an A2 that is y-like. Okay, so this is a dy0 thing that's pointing positively on the y-axis, and here's one that's pointing positively on the x-axis. So B1, very x-like, okay, and it's the one with a plus sign, and there's the y one right there that's got a minus sign. Okay, so just knowing the group theory, I could have gone this way and gotten the eigenvectors of this and been done more quickly than going and writing everything out and then doing the diagonalization of brute force. Okay, so this is a really good one just to get your feet, your toes wet as you go swimming in the massive numbers of high quantum states that are waiting to get solutions to them. Okay, now angular momentum 2 is a little bit more difficult, you see, because it's got 5. There's its matrix using an arbitrary A, B, and C. Okay, and we've written out part of this one. Well, I guess we haven't. We stopped it. No, we did. We went to as high as 2, I think. I'll have to check. But in any case, here it is. Okay, well, this one is a little less diagonal than the other one is. It obviously requires some work. We're now working in the full basis of all 5 of these standing D waves. Okay, and the question is, what linear combinations of those are going to give me an eigenvector? Now, when I look at the correlation table, it tells me something right away. It tells me that I can be sure of what my eigenvectors are for this, this, and this, because there's only one of them. But this one, there's 2. The A1, there's going to be 2 ways to make an A1. That means there's going to be a 2x2 blocked matrix that's going to come out of there. The other 3 are going to be on the diagonal when I use symmetry projectors from D2. These are the 2 right here. 2, 0, and 2 plus minus 2. Those 2 are going to play with each other, and they're going to depend on what these values of parameters are. You see. So there's freedom there, you see. When you have a correlation table with a number besides 1, you've got some extra work to do, and it tells you how much work you got. You got a 2 by 2 matrix to solve. These, you don't need to solve anything whenever you see 1. Now, as you can see, as we go up here, you get to quite a number of things. You're going to have a 4 by 4 matrix for this one, and this one, and this one, and you have only a 3 by 3 for that one. But that's going to be for a computer to take care of, right? If you're into the way they normally do problems like this. But these things are already eigenvectors. You see, these, and this are already eigenvectors. And so when you put that set of numbers into this one, that is, if you write them out as a transformation matrix, you will reduce this thing to that. And there are the two on the ends. Those are the, this guy, and that's the one that's last, you see. And it's got a off-diagonal element that is equal to the difference between A and B. So if A and B are equal, it's gone, but that's a symmetric top. Okay? So this is the grinded out work that you have to do if you really want to get all these states down to the last decimal, you see. And we're only on angular momentum 2. Go to 3, 4, 5, 6, and then 50 and 100. A lot of computational work with very little visualization. We need to be able to visualize these things as well as we can visualize this one. Now when I get done here, I see an A1 in there, okay? As far with respect to D2, that's definitely A1. No matter what 180-degree rotation I do, they go into each other without change of sign, okay? But when you look at each one of these, you can see who's going to change signs just by looking at the character table. And that's the way you assign the fact that this is an A2, this is a B2, this is a B1, and these two are A1s who get mixed with each other. So we'll get linear combination of something like that with a little bit of that thrown in. That's allowed by D2. So Murphy's law says if it's allowed to mix these two, they'll mix. And with an asymmetric top, they guarantee they will. Okay, so that's kind of an interesting little thing. So let's go ahead and do that 2 by 2 out just to see what the mixtures are and what the eigenvalues do. The eigenvalues are going to change now. We've got an avoided crossing, okay, coming up here. Okay, as I vary A and B against each other, something's going to happen. Okay, well, this is what happens. Here's an asymmetric top in the middle. Everything in here is an asymmetric top, but on the edges, I've got a prolate top. Okay, that's a top where I've got A and B equal to 2 and C is equal to 3. A and B are equal to 2 down here, and C is bigger. And then what we're going to do is we're going to subtract x from A and subtract x from 3 until they meet. Okay? When they meet, I'm going to have B equal to B and C equal, and A is going to be lower, which will make an oblate top. So here we go from being a prolate to an oblate, and right in the middle, at the most asymmetric top, that's the rotational energy surface for a perfectly asymmetric top. Now, the avoided crossing is just between the A1s. You see the two A1s. The B1 and B2, they start degenerate, they end degenerate, and they're degenerate all across. The A2, it just goes a straight line. It's when they curve that they're mixing their content, okay? This one is changing from something that has a lot of angular momentum in the body frame, plus or minus, okay? And there's two levels here, you see, that are going along here. And there's two levels here that are going along as well, you see. But this one is changing from the n equal plus and minus 2 to n equals 0. I sort of colored it to indicate that it's changing its character and getting more and more 0-like. While the one that started 0 is getting more and more 2-like. You see, it's going from red to blue if you want to color those things that way. So this is a lot of insight into what happens if a molecule were to change its symmetry from, say, prolate to oblate somehow. Now that's hard to do, actually, as it turns out. But what we do is we consider whole families of molecules that fill a scaled plot like that, and then you can see this that way. Okay. Well, now I'm going to take on high J.
Sorry, what was the horizontal axis? Horizontal axis.
The horizontal axis, right here, that you're talking about, this,
Yeah.
that's just 12. That's the energy value with this particular scaling.
Yeah, something is changing. Are we moving in the on the?
What we're doing, this is the x-axis, okay, the horizontal axis, and its quantity is equal to the amount that I'm subtracting from the parameter A to make it asymmetric,
Yeah.
while I'm also subtracting it from C, because I want these two to meet. So at x equal a half, I'm right here. And then at x equal 1, now I'm an oblate. You see, now I have that value. Actually, that is a typo. I'm going to go back where it's right. That's what I have.
Yeah.
You see. Okay. I got to change that. Yeah. I forgot to change it on the copy slide. Okay.
So
So
did you catch it
Yeah,
that
yeah,
time?
does that make sense? Yeah.
That's a
Okay.
trick.
Now we're going to do something like this with j equal
0 to
20.
1.
Yeah.
It's x.
Yeah. It goes from 0 to
It's
1,
X
and
from 0 to
there's
1.
the extreme where they're really avoiding, and then they settle down, you see, at the end there. Okay, now this is from Springer Handbook. The most recent one is 2005, and we were glad to be able to get this in there, but unfortunately, I think they made it worse than the one that was in 1995. They do this kind of every 15 or 10 or 15 years. And what I want to show you is a rotational energy source connected to, and this is j equal 10, connected to the thing we just did. But this time we're just going to maintain that most asymmetric top and see what it's all of its load. You see the A1s and B1s are in there, and they're making little clusters, you see. The symmetric top is a doublet that's absolutely degenerate. These have little tiny splittings. This one only has 26 kilohertz. This one that you could just barely see here is 1.5 gigahertz. Okay? This one's about 10 gigahertz right there, and then talking about many gigahertz, we're talking about typically microwave spectra for rotation of an asymmetric top, like water. Okay, so this is a spectrum of water, basically, for j equal 10, so it's called qualitatively. Okay? So what I want to do is tell a story about that that makes sense. Here are the extremes. Here I have the thing rotating on an axis of an oblate top. Okay, and I'm talking about the x-axis now. D2 is the supergroup for a subgroup C2 on the x-axis. We've got 3 different C2 subgroups in the D4. I'm sorry, the D2 group. We've got 3 different C2 subgroups. One for X, one for Y, one for Z. Okay. And the correlation for C2X at even and odd with the D2, A1, A2, B1, B2 is this. And you can see that very easily just by looking at the X correlation table here, noticing A1 and B1 are both 1, okay? A1 and B1, okay? That's the way it was labeled, right? And then A2 and B2, they're both minus 1 with respect to X. So there's where A2 goes. It goes in the odd column, okay? Now the actual spectra of this molecule, if it's asymmetric, you see, is going to be these two clustered, you see, the even cluster, and then this will be the odd cluster. That's on the x-axis, okay? So we're going to get a mixture here of red and sort of a pale yellow, and this one's going to be a pale yellow, green, and a blue. Those are indicated by an orange circle at the bottom there, and then the next stop out is one of these, and then another orange one, you see, right here, and then another one of the cyan ones, you see, and then one more sort of orange one that's looking a little sick, and that's the one that's going to be split a little bit more, okay? And that takes care of the x-axis. That's all the activity associated with the local symmetry on the x-axis, C2x local symmetry, okay? And that corresponds to the molecule rotating like that, rotating like a boomerang. That's the most stable rotation that this molecule can do. When I was throwing this thing, you see, I pointed out first that that's the most stable, and that's what we're talking about, where this is the x-axis. That's y and z, okay? So that's as low as you can go for a given angular momentum. That's the valley, lowest energies region. Now, there's another set on the other side. There's pairs of them, you see. So that's what makes these doublets, really. But the doublets, you know, are only approximately determined, but the approximation can be enormously fast. Now, the other extreme, the top, okay? This is C2Z, z-axis, okay? On the z-axis, okay, where I have this kind of rotation, crankshaft rotation, that's also reasonably stable, but if I perturb this thing, it's liable to fall down the rotational energy surface, you see, maintaining the total angular momentum, but losing energy. You will end up, if you set a satellite in the sky rotating like that, it is liable to turn, and say I'm rotating like this, so the angular momentum is this way, it's going to turn into that. If the satellite is loose and losing energy. Can't lose angular momentum, so it's got to stay on the surface, but it can fall into the valley. So this is kind of an excited state, you might say, when you're up on a mountaintop. Now in between those two, as this thing, say, rotates and starts to creak and do all sorts of things, it's going to pass through this. This is a thing that's totally dynamically unstable. This is the one that does the flipperoo back and forth.
I saw it there.
And that was a pretty good one right there. I'll go with that. And while I'm at it, I'll just show you an asymmetric top doing it very periodically on an air cushion with no appreciable torque on it. But you can see it's on a nice air bearing there, and it's got a north pole and a south pole on the y-axis, so you can see what happens. I'm going to start the thing up here with the north pole facing you, more or less. Okay, I get that going, and it looks like it's going to stay, but then all of a sudden, balloon-putty, now it's facing me. And now it's going to come back and face you for a while. Now that's actually a very chaotic bunch of motion that's going on there, because there's little turbulences and things like that. If I was in a space lab, it would do it perfectly. So in principle, this is something that happens very well with no torque. Okay? So that corresponds to motion. If this is totally classical, this quantum has 10 to the 38th or astronomical number of quanta, but here we're talking about quanta 10, okay? And we're saying if I get really close here, I can stay there for a long period, but at some time, if I'm over here in the valley, I take my left hand, I'm going to take off this way and go around that thing and then get stuck on the other side for a while, and then continue back and come back here and get stuck there again, and then come back. But if I'm up here, okay, in this region right here, I use my left hand like this, okay. Well, I still go this way, you see, but this time I come back around the top instead of coming around the bottom. So it's really an amazing classical motion. But now what we want to do is we want to make that into a quantum mechanical picture. And that's where it really gets interesting. So we don't see any clusters like this one, A1, A2, or B1, B2. We don't see that in the spectrum. Here's the spectrum, this time the way it was in the original paper. I've got A1, B1, A2, B2. A1, B1, A2, B2. That's even, odd, okay? And then I started seeing the splitting between A1, B1 as I start one more time to make an A1, B1, 2, and then I have A2. Now A2 is one we call color green, and that corresponds to that trajectory on the asymmetric top that was this big green separatrix. It's a dotted curve here, you see. It's this dotted curve right there that we would be sitting right on if I could actually set the quantum state right there. I would have a wave function that covered that entire separatrix, completely delocalized. That would be what the wave function would look like if you plotted it out. Okay? Now, if I'm close to the top like this, that's as high as I can get. If I'm close to the top here, just follow the line down and you're doing this kind of cluster. You're doing a B2A1 cluster. B2A1. This is an even. It's J equal 10, so that's basically K equal or N equal 10. Even. Okay? Then the odd one that comes next is 9. All right? 9 is this one right here. That would be this one, B1A2, you see, is the next odd fellow. And then we go once again, A1, B2, in that ordering. And that's the other thing that's really amazing about this thing. These things really know where they belong. This begins to answer my question about beta stuff. You know, what's going on, all those levels? How are they connected? This is showing, at least for D2, a pretty good picture of that. Okay? And we know we're just not getting any stable rotation like that. We are getting this in the valley and this on the mountain. With very different splittings, ranging from 26 kilohertz up to more than a gigahertz. And there's the picture. Now I like to show a better picture of this too. This you see is, I think, hard to read. They did a fancy art job on it, but it makes it hard to read. Now, here's where I say, if you can change A and B, or B and C, okay, relative to each other, you'll change this angle. This angle is the arc tangent of A minus B over B minus C. And if you want that to be 45 degrees, you want A minus B to equal B minus C. So that's what we've got here. We've got a nice 45-degree angle between the separatrix, which are circles. That's something the geometry of this thing shows. Okay, so there's a more modern picture of the asymmetric top, and then a momentum cone with just a little bit of error in terms of where it hits the circle, and then more error as we go, and that just means you're mixing more other quanta into this. Now here's what, remember we did a correlation of levels before. This is very similar to that. Okay, and here's where you change from one type of cluster to another. The red and the orange are split to make a purple and, let's see, this one is a red and a blue. That would be, I think, let me check to see if I've got the coloring scheme right here. This one is yellow and magenta, I guess. I may have this turned around. It looks like I do have this turned around. This is the should be a picture of that one, and I've got to look at this again. Anyway, that's the advantage of using colors to label which kind of clusters you're making, you see. And here is the most asymmetric top right here, okay, halfway. And then it turns into a blade. So there's the oblate and there's the prolate. So we're using a sort of color mixing scheme here that I say it's reversed. I've got to figure out what that means. I think I did change the colors from what we do. Okay, now here is the Big Daddy. This is going to be a completely symmetric rotor. That's what it looks like, okay? So this is going to be a molecule that has either, you can use this symmetry, but there is a SF6 sitting around here somewhere. Do you see that? Thank you very much. You see, this is the molecule we're actually thinking about, and I'll show you spectra of that one actually, but we're going to look at a numerical treatment of this one. So this basically is an energy surface. If the molecule does not distort, that's the only Hamiltonian we have. Just have one parameter for rotation. Inertia the same in all directions. And this is something that describes how it distorts. This is the lowest order, lowest rank tensor, rank 4 tensor, that can have octahedral symmetry, which this thing clearly has. And it is describing, with a positive sign here, a rotational energy surface that has peaks in the directions where the atoms are, where the radial bonds are, where the bonds that would stretch, if they could, under rotation. And the bonds are very strong, so they do not stretch much when you turn the rotation up, in whichever direction. This one right here corresponds to it doing that. This one over here corresponds to it rotating like that. This one over here corresponds to it rotating like that. You see, there's 6 different ways that this thing can rotate with a quantum number N4, this is molecular K being used here, equal to J, which is 30. This is a J equals 30 rotational energy surface. And the idea is that if I were to put this on an axis that would rotate it around the threefold, the 1, 1, 1 direction, and there are 8 different ones of those, that would have much more chance to distort. And if you distort this by making it higher inertia, you make it lower energy. Remember the inverse, 1 over 2I. I now getting bigger means the energy is getting less. So down you go into a valley. Okay? Now it turns out that the same shape surface you use for almost all the J's up to very high, so high we haven't actually measured a case where the surface starts to change to something else with higher rank tensors coming into play. At least for molecules like this, these heavy tops are actually, because of their inertia, very slow. The rotation is very slow compared to water or molecules that are light, like methane. CH4 is very light, it goes very fast compared to these things. These are heavy tops. So what we're going to do is we're going to use the tensorial description of these angular momentums, and that's a real shortcut for doing matrix calculations. And that's going to be a little bit of the topic of our final talks on this, and we'll show some other stuff that they do as well. But in any case, what I'd like to do is just do the semi-qualitative analysis of J equal 30, and also a little bit later J equal 88. We'll look at the actual spectra for P88, and we'll see also one that's closer to the thing that we just looked at for J equal 30. But I really want to visualize the J equal 30 quantum levels. But before we do that, we're going to do the same thing that we did here, character analysis. This is the old-fashioned beta stuff. I want to do the beta character analysis, And apparently he was the first to do the octahedral symmetries in a long time ago, late 20s or early 30s of 1900s. This is out of the PSDS textbook, 1993, listing the characters that are all given by this formula. What now we've got to do, as you remember, 120 degrees, 180 degrees. There are two kinds of 180 degrees. And then there are the 90-degree rotations, X, Y, and Z. These are the I1 through 6. These are the R squareds here. This is all stuff that we talked about before. And there are the old characters that we're going to correlate with the rotation 3, or orthogonal group 3 as well. It's just a parity has to be added. And I've actually put the parities on these things here. So here, angular momentum 0 is the only one that's obvious, and that's the A1. That's A1 right there. It corresponds very nicely to that. But then from there on, it's trial and error, or use the formula to calculate the frequency. Well, angular momentum 1 is just 1. That's T1. So there's a triplet for the octahedron, and it's a triplet as well for the big group, O3. But then 5 splits. 5 splits into a doublet, that's E, and a triplet, EG and T2G. Okay? Then after that, angular momentum 3, okay, that's the octupole. This was the quadrupole. The octupole split has 7 components, okay, with lots of 1s and minus 1s here, which correlate with this one. That's an A2, a T1, and a T2. And I put a U on because for a single orbital, single particle orbital, that would be odd. This one, they alternate, even odd, according to J. And then finally, the G orbital, okay, 4, has 9 components. And there they are, okay? Well, you can see this gets pretty complicated pretty fast. And then it all starts over again, right there. This is an extra A1, and then the regular representation of octahedral group, which has a dimension of 3 squared plus 3 squared plus 2 squared plus 1 squared plus 1 squared. That's 24. 24 is the order of the octahedral group. And the squares are just there for the projectors, that you have to have 3 projectors for each of these guys, okay? And each dimension has 3. The Mach principle demands that counting, you see. So the next thing after that, you see, is going to be the same thing with a 4 here, and I'm taking 1 off of there. That's this guy. So this whole thing repeats after 12. All right? So this is going to happen over and over and over again. We're going to make use of that. This is the way it's going to play out, so to speak. Now, the L equal 2 splitting, this is a crummy picture of the 3rd entry in the correlation table, EG plus T2G. I put this one up here since we are sitting over a laboratory that uses this every day, and all they're doing is playing with the amount of the triplet that sits between the axes of some octahedral or cubic shaped thing, and the electrons that sit on the axes, that is usually pointing at some neighbor there. That's a high energy state. This is a low energy state. They play with these, plus they split these guys a little bit. And they're doing it with all the electrons in the solid, so it becomes very powerful. You see, it is very something that people had been dreaming of doing for years and years, and now we're doing it finally. Okay, and this is just fun. I call these prayer wheels or mnemonic wheels. For example, I look at that correlation table, I can show that for J equals 0, I go from where it says J equals 0 to J equals 0, that's A1. And then the next stop is an odd one, there's j equal 1, I go until I get j equal 1 equal, well, it's t1, you say. And I come back here for j equal 2, okay? And there's j equal 2 right there, and j equal 2, I go in that direction until I hit a j equal 2, which is right there. There's t2 and e coming out of the d, and so forth. As I run up my j, there's the way, that's the code, the genetic code of the stuff that's coming out between angular momentum 0 and 12, and then it's going to do it again from 13 to 24, and so forth. Okay? So this is what we're going to be faced with, and it's analogous to what's going on in D2, D3, D4, D5, D6. This is a D6 wheel right here that's just going through the A1, E1, E2, E3, E4, then B1, that's a band, and then comes a gap, and then you start over again now with B2, and you count backwards. E something, in this case 2, 1, and then finally A2, and then you start the whole thing over. So this is band theory, this is cluster theory. They're sort of the same physically, except that the latter is a lot easier to play with because angular momentum, total angular momentum is really a good quantum number. So let's look at j equals 30 fairly closely. Okay, angular momentum cones and all that are going to be placed. What we have to know in order to understand what's going to happen to these levels quantitatively is that the distance from the quadrilateral or tetragonal four-fold symmetry axis and the nearest separatrix. Separatrix is that green thing that we were noticing on the asymmetric top, where the rotation would be totally unstable. It occupies a very small part of this story, but nevertheless we want to know how far away from it are we. And then on the threefold axis, the 1, 1, 1 direction, like right here, how far am I to that danger place, that separatrix, where I'm going to get thrown around the planet instead in a very chaotic sort of way, as opposed to just doing some nice precession in my little valley village here. Okay, so 19.5 degrees is a key number, and 35.3 is the key piece of geometry that we'll be using. And it's the same for that one. So once we get this down, we can do all of these orbitals very neatly. So here is the actual spectrum corresponding to each of the little pathways on this rotational energy surface, which is the same shape and symmetry as the actual molecule itself. And it represents where the angular momentum J will do its little dance around using the left-hand rule, okay, going this way on the mountains and going this way, you see the arrows there, in the valleys, okay? So the mountains have J's that are precessing like that, classically, okay? But they have quantum levels that are indicated by where the angular momentum cones go through, more or less, okay? So we've seen this already. This is J equal 30 cones. I showed it before with its uncertainty angles of 10, 18, 23, 27, 31, 34, 38, okay? Now, what this is telling me is that if I have an angle of 35.3 for the mountains, that's the fourfold symmetry things, I could maybe go to 34.9 degrees and be still on the mountain, not have fallen off, because I'm less than 35. I'm certainly safe with 31, and boy, these guys are way smaller than 35. Okay? So, that's where it's going to come apart. There's a cutoff between those two. Okay? So you've got 1, 2, 3, 4, 5, 6 things that are really happy with mountains. And that's what we've got for clusters here. 1, 2, 3, 4, 5, 6, then it's very questionable. Okay? 30 is 2 mod 4, so that's a 2 mod 4 cluster. This is a 1 mod 4 cluster. This is a 0 mod 4 cluster. You familiar with that one? A1T1E? That was the first one we looked at. Okay? So there are the 6 guys that correspond to mountains. Now, valleys, very persnickety. Their population is small because they only have 20 degrees. Okay? So, well, what can I do here? I can certainly get a 10 in there. I can get an 18 just barely. 23 too much. So that's not going to be very viable. So I only see 2 possibilities. There they are. It's questionable. Just 2 guys. 0 mod 3 and 1 mod 3. Actually 2 mod 3. It's minus 1 mod 3 because you count down from the outskirts. Okay? Now here's some actual spectrum of 30s. This one is a tetrafluorosilane. And you can see 1, 2, 3, 4, 5, 6 starting to come apart, but then there's the spectroscopy region, and then 1, 2 on this side. Here's 30 right here of cubane. Cubane is a very weird high explosive, but it has 2 on the 3-fold axis and 1, 2, 3, 4, 5, 6. And then next door is 31. It's not too different. It's starting to grow a few more alpha separatrix. Now, you can actually fit these things on top of this computer spectrum. There's very little deviation from what the experiment gives. So we're using these angular momentum cones with very good precision. Good to 1 or 2 figure accuracy right up to the separatrix. Then from there on out, they're right on. The precision goes up with the splittings. Okay, the tunneling gets really slow out on the edge there. Okay, so these are the clusters that we're talking about. You remember these correlation tables for C4 to the octahedron. There's C4, there's the octahedral, right? There's that 0 mod 4 cluster of A1, E, and T1. Then you have a T1, T2, and then followed by the 2-4 cluster, A2, E, and T2, and then another one of these, and that's all that happens. It just keeps doing that, as long as you can stay on the mountains. And then here's the valley, you see. Once again, 2-fold axis, we can't manage it. It's a separatrix going through there. We can't support a localized state. So we don't see these in most of these molecules in their ground states, ground vibrational states. Okay, now let's look at 88. That's pretty spectacular. We've seen this before, but I want to mention a few things before we quit here. And that is that these primary species get destroyed by this whole process. And as you increase the distance from the separatrix, the chance of them getting destroyed by hyperfine effects is very high. But in any case, there's a region where you're sure they're not mixed, and then you're a region where you're sure they are. And that is the whole nother story. This is something for another semester. But I think this is something that's just not been looked at enough, and we need to know more about it. So we do this so that we can really understand the molecule when it starts to take its own NMR spectrum. That's really what's happening. This molecule has a little residual current due to its rotation, which creates a magnetic field, which is like an NMR field, and it causes the nuclear spins to start to dance. And the question is, whether they dance to the outside, that's the laboratory, or to the body, the inside. These are all dancing to the body, and they have destroyed these species by doing that. They've mixed them in a way that Hertzberg said would never happen, but he'd never, of course, thought of a process that we're talking about here. In any case, this sort of sums it up. You draw angular momentum cones and lay them on a plane that goes through the major active axes, the 3-fold axis and the fourfold axis, and then put the cones down there, and just wherever they hit the surface, you just come back, and that's a spectral line. I mean, they literally fit the spectrum. This is actually fortuitous, because the idea is the rotational energy surface of the ground vibrational and the excited vibrational state is the same shape. So the geometry is the same. So the Hertzberg rules still apply near the separatrices, you see. As long as this thing is tumbling wildly, the species won't mix. But when they get stuck in their local symmetry, then they start paying attention. So this is a blow up of that same thing. So that's what is waiting in the future to really understand a good deal more. Okay, this is something that's in the handbook. I just show it to you real quickly. This is a tetrahedral molecule. You use the same stuff. A tetrahedron and a cube, one's half of the other, and they're conjugate to the octahedron. So a whole bunch of different symmetries and molecules use exactly, with a little change in notation. I use F's instead of T's, but aside from that, it's pretty much the same. You use the same deal. These are two figures that are from 95, 96, and 2005. And there's a pretty good description of this, but it doesn't have all the details that we've been talking about today. There's not room for it in a simple chapter. So that's it for today. If there are any questions about this, certainly entertain them. But that's what we're trying to understand. It's an amazing thing. And you realize this is one rotation, 88. It's got all this structure. The next door one, 87 and 89. Different, but the same idea. All the way down and up to 150. This is happening. The tunneling parameters range over from 7 times 10 to the minus 12 hertz. That's, over 10,000 years. So the tunneling is really down to the point where the hyperfine has completely wiped this thing out. They go up exponentially as we approach the separatrix. Until finally in this region we're talking about half a megahertz or 1 megahertz right here. And then it goes back down a little bit. Not as far, because the three folds can tunnel a lot. So you only get down to about 3.6 hertz. But that's really small on a molecular scale. So things are varying over 15 orders of magnitude. There's no system that we know of that has such a pure example of tunneling at many orders of magnitude that we can play with. And we can do it with optical infrared spectra. And we can make it really quiet, because a molecule can be placed in an environment that doesn't have noise. So it's only its motion. It's all completely body until you touch it with a laser. Whereas a solid will never, it'll be really hard to get that. Really hard to get that sort of behavior in a solid. So here's an opportunity to do some really pure quantum mechanics that involves the spin, all kinds of things that we have. One of the problems is you really have to use relativity on these things. Relativistic effects are important, even though the things are just creeping. So the physics here is really heavy. And that's why Abe Zoka looked at just the beginnings of this and said, I'll do it in my next life. But it's kind of nice to have kind of your own field, and that's what this is. But it's spawned, you see, a way of understanding symmetry in ways that weren't there before. So we owe, it's an experimental science. Physics is always experimental science, but the theory is important too. And it's easy enough to go and put all this stuff on a computer and get the numbers. But the computer isn't going to tell you what's going on. And that was a real lesson that I think I learned first, and then I taught it to the people that are in this field, that the way to visualize the thing is not going to come from a computer in the form that we have them now. Now, later on, we make some intelligent robot or something that would go in there, say, hey, did you notice those clusters, and you know what that might be, and blah, 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 right? And that's very much a human thing. And the clusters existed in the literature from 1970s until we started working on it in the mid-80s. At that time we said, hey, this is why they work, and here's why, and here's how, and all that. At first it was, rebutted. It said, oh, come on, it can't be that simple. They were looking for big symmetry groups that would have huge irreducible representations that would account for degeneracy of 6 that you see there. 1 plus 3 plus 2 is 6. 3 plus 3 is 6. That's the number of mountains on the rotational Lagrange surface, the number of atoms on the outside. Then over here, that's 8. 3 plus 2 plus 3. 1 plus 3 plus 3 plus 1. You see irreducible representations of the cubic group. Sort of, I like to say, living in sin. They're living in, they're unmarried, but they're living in the same house, you see. Why are they there? You see, that was the question. And why are some of them really close? You see, and others not so close. Why those particular ones, you see? So they were looking for huge groups that would give them, just like particle physics, you go to U3, U4, U5, you look at
Pluralities.
those, groups. All symmetries we still don't understand why they're there. And what I was showing was that these were degeneracies due to breaking of symmetry, spontaneous breaking. This is clustering, unsplitting, that occurs because you're doing the inside job. You're doing the stuff for the body. The body is itself having this symmetry, and the symmetry is getting stuck in subgroups, localizing. And the number of ways it can localize is a degeneracy that is a cluster large, is larger than you would expect if you didn't know that this was going on. So I hold this up as a really good lesson in symmetry, but also it's going to be more lessons in physics as we get better instruments to look at things like this. Pretty good job already, but it's always a chance to get better. And that's where solid state comes in. Solid state can make instruments with really pure frequency combs and things like that allow us to tune our way through this. It's up to this point, you've just been lucky if you had a frequency to hit something. This is 16 microns, and it's kind of sparse, but it was enough to go. And then we make laser diodes to do that, and so on. It was a real technological hurdle to get the stuff that gives these. These people are to be credited for doing the FTIR and the laser diode spectra.
Bill, did you say that we, at this point in time, humanity does not have the ability to do these sort of higher resolution experiments?
Well,
we used to?
The really high resolution
Yeah.
is done by a spectrometer that exists only one place in the world.
It's still up then.
Christian Bourdais' monster CO2 lamb dip spectroscopy device in University of Paris at Villetaneuse. I guess it's University of Paris number 17. Okay, and he conned the French government out of millions of dollars to build this because the idea was that they could use the spectra to separate UF6 235 from UF6 normally 238, right? And that's what Los Alamos had been doing for years, and that's where this originally came from, and that's where these people come from. They all worked at Los Alamos, and they worked on the isotope separation project. It's called MLIS, Molecular Laser Isotope Separation. So it has an unfortunate father. That is, making what we know to be fairly harmful, and that is nuclear radiative material. They were doing it to plutonium as well. Plutonium makes hexafluoride very nicely. So that spectra that Bourdais has at such high resolution requires a 31-meter chamber with two mirrors at the ends whose radii is many kilometers. So he's got this light going back and forth, you see, and that way you can get rid of the Doppler shift. Then you can look at it and you can get rid of the relativistic shift as well. I mean, you can show what it is and read it. And that's all in doing, finding these things, you see. And all of this stuff, I just did sketches of it, and when they were doing their experiments, they were literally sitting there looking with my paper saying, oh, here's one, you see. The pattern's very identifiable, you see. In a huge field of spectral lines, you can zero in with the instrument they had. Now, the instruments we're making now, they're very tunable. They're fairly wide. These guys were typically 10 to 50 hertz error, which at tens of 20s of terahertz is pretty good. So you're talking about 1 part in 10 to 12. The solid-state devices are not so good, but they can tune anywhere. These you really had to push to tune. So that's an experimental fact. Now, as we get better and better at making the frequency comb lasers and stabilizing them, then we come back and look at things like this using difference spectra, making differences. We can come down and look at the infrared again. So that's waiting. Now, in doing this for buckyball, we'd like to do this for buckyball. We'd like to do analysis like this for buckyball. I've got lots of theory out there on it, but the parameters I don't know. The parameters have to be, either calculated by electronic structure programs that are far beyond anything we have now, because the ones we have now are not as precise to give those numbers. So experimentals are still going to be needed. And then the other problem is to cool the molecule so that I can get rid of the hot bands and just look at single quanta of vibration. Buckyball is so big that the inertia is so huge that the splittings, the rotational splittings, really tiny. And then all the vibrations are going at once, so you're lost in a forest. You got to cool it, and then you got to have a spectral device that can handle that. Very, very, very high resolution. Okay, so with that.